30 years ago, we knew of 0 exoplanets, but in this year of 2021, we now know of over 10,000 exoplanetary candidates, of which the vast majority are likely real. The current detection rate equates to about 4 new exoplanets discovered each day. Planet detection has become routine, even ordinary and mundane. And so what once was front page news now often barely registers as worthy of discussion in astronomy departments these days. 10,000 exoplanets, and yet despite this, we know of just a single exomoon candidate, Kepler 1625b-I. Moons continue to elude us, but why and how can we change this? A decade ago, I finished my PhD. The transits of extrasolar planets with moons. Over the course of my PhD, I worked hard to develop new techniques for discovering moons using transits. Even back then, it was clear that the transit method was the future of our field. Blinking stars caused by orbiting planets eclipsing in front of them. With NASA's Kepler mission about to launch a space telescope dedicated to exploiting transits, I remember there was a sense of optimism about exomoons too, what treasures they might reveal. Kepler and its successor, TESS, are undoubtedly successful missions with a catalogue of over 10,000 planetary candidates to show for themselves. Some of these planets are as small as Mars and even our moon, so why didn't these missions reveal hundreds of exomoons along the way? Part of the explanation is likely that many of these newfound planets are simply too close to their host stars to hold on to large detectable moons. For all of these successes of these modern surveys, they have an inherent bias towards finding planets which are huddled up against their stars in tight, compact orbits. But despite this, there are still hundreds of planets in orbits comparable to that of the Earth, or even wider, including many gas giants. And so the question remains as to why more moons were not found. Another part of the explanation is surely just that the amount of brains, time, and effort that we are spending working on this problem is simply insufficient. In the exoplanet conferences I've recently attended, there are hardly any talks about exomoons. There are very few papers written about this subject and hardly any scientific funding. Is that because planets are somehow inherently more interesting than moons? Or is it because the associated risk of researching them is inherently far higher? Given the highly competitive nature of our field's job market, it's easy to understand why working on unproven ideas could be perceived as simply too risky. And finally, there's the question of methodology. Perhaps we are simply not looking in the right way. 10 years ago, I suggested that there are 2 key techniques that we could use to look for exomoons. The first of which was to look at the gravitational wobbles that moons induce on their host planets, an effect that we call transit timing variations, or TTVs. Planets should orbit their star like clockwork. 1 transit per planetary year, but a moon slightly tugs on the planet, disrupting that regular timing by seconds or even minutes. This was unfortunately too successful for its own good, because we now know of hundreds of planets which show these TTVs, but distinguishing the cause turned out to be more challenging than anticipated. Notably, another distant planet in the system can also cause these kinds of wobbles. Recently, I showed that there is some hope of disentangling the effects by looking at the frequency of these wobbles. You can check out our video about this to learn more. The other method that we'll focus on today is to look for the transits of the moon itself. Look, if the planet transits across the face of the star, then the moon must as well for most configurations. Now, yes, these dips will clearly be smaller than that of the planet, but hey, if Kepler can detect Mars-sized, even moon-sized dips, then surely it should be able to detect exomoons via the same technique. What looks good in theory often pans out worse in practice. You see, real light curves don't look as nice as this. Noise gets in the way. To see this, let's look at Kepler 37b. an exoplanet that's about the same size as our moon and discovered by Tom Barkley and colleagues using Kepler in 2013. The planet orbits its star once every 13.37 days. That's its year, which means over the 4-year window that Kepler stared at it, it should have completed more than 100 separate transits. Now let's look at the data. What we're looking at here is the brightness of the star over time, where the other planets besides Kepler 37b have been removed to make things nice and clear. Now, if you're looking at this thinking, I can't see any dips, this just looks like a fluffy line, well, you're right. The transits of Kepler 37b are almost impossible to see. To help, let's try zooming into the location of just one of these transits. Again, even now, it's very difficult to see a dip here. If this was how astronomers looked for planets, then Kepler 37b would have never been found. But astronomers don't look for individual transits, no. Years ago, we developed a clever trick to uncover these tiny signals, called folding. Folding works like this. First, let's imagine that I have a sequence of 4 transits represented by this paper chain that I'm holding up here. The trouble is that the individual events are often just too small to see given the noise level. But if we fold this paper chain up, putting each transit on top of one another, we end up averaging out the noise but maintaining the crisp, clear signal of the transit. Now, rather than looking at just one transit, I'm looking at all 4 simultaneously. And so since there are 4 times as much data here, then the signal to noise goes up by square root 4 or twice as much. The secret as to why this works so well is because the shape of the transit is the same each time, and by folding the data in just the right way, I preserve that shape. We could say that the transit is coherent upon folding. Astronomers use this trick all the time to look for planets. You guess a possible orbital period for the planet, you fold, and then you see if anything pops out, and then you move on to another guess, often visualized like this. So coming back to Kepler 37b, if we fold her transits upon the true period, that's remember 13.37 days, then we can see just how well this works. Because there's over 100 transits folded here, the signal to noise is now 10 times higher, clearly visible by eye. But if I fold the data on the wrong period, say 12.37 days, then you can see that I get a complete mess. So this method is powerful, but you have to look carefully through each possible guess to find a planet this way. So yes, Kepler can detect moon-sized planets. Kepler 37b demonstrates that. But crucially, Kepler can't detect the actual individual transits of such small worlds, only the combined fold of them together. Now let's come back to moons. The problem with moons is that they're slippery critters. They refuse to stay in the same place. So in transit number 1, the moon could be a little bit ahead of the planet, represented by this pink paperclip, and thus come in earlier than the planet. But next time around, the moon could be a little bit behind and thus come in later. This means that the transit shape is constantly changing. Now, this doesn't happen when we're doing vanilla planet hunting because the transit signal just looks the same each and every time that we look at it. And that's crucial as to why the transit folding technique works so well. If the signal keeps changing, then we try to fold this back up, you end up averaging not only the noise, but the signal itself. Unlike the planet, the moon signal doesn't neatly add together. So frankly, for 10 years, we've had no way of solving this problem. Yes, you can create beautiful folded transits for planets, but for moons, you just can't do it. And of course, this limits our ability to look for exomoons. If we can't fold, then we lose one of the most powerful weapons in our arsenal. Well, that is until now. Thanks to support from many of you, I've been able to spend some time revisiting this dilemma. You know, I've always believed that there's just about nothing that the human mind can't solve with some time, some quiet, and a lot of coffee. And for years I felt like there was a solution to this problem, just one that was somehow out of grasp. And look, if no one else is gonna solve this exomoon problem, then hey, I guess it's back down to me once again. So today I'm thrilled to be able to tell you about new research that solves this exomoon problem. A fold, once for the planet, and twice for the moon, what you might call transit origami. Before we explore this solution, I just want to quickly thank the sponsor of today's video, that's Morning Brew. So I have kind of a small obsession with efficiency and optimization. I think astronomy teaches you how short and precious our lives are, that you need to make the most of every hour, every minute as efficiently as possible. That's why Morning Brew is great. You can waste away your morning just aimlessly browsing social media, or you can sign up and start your day with tight, concise summaries of everything that you need to know in the world of tech, business, and finance. Morning Brew is a way of hacking your efficiency. It's just the easiest way to keep up with everything going on. For example, my favorite article that I read last week explained why so many records are being broken in track events at the Olympics this year. Look, Morning Brew is totally free. They're supporting science communication through this sponsorship, so please check them out, see if they save you some time each day by using the link down below in the description. A few years ago, I visited Japan for a conference and got to spend some time visiting tea houses, ancient castles, and beautiful gardens. I remember one day watching a Japanese woman delicately fold a piece of paper, crisply scoring the edges, folding them in intricate twists until finally she held up a flower. In a way, the flower was always there, just hidden inside the paper, but she found the right way of folding the paper in order to reveal it. During that conference, I discussed with a colleague the problem of looking for exomoon transits. They suggested a computationally intensive solution. Look, just try every possible moon orbit, every inclination, every eccentricity, every orbital period. What astronomers might often call a brute force approach. I shook my head and explained how we'd been doing just that, but brute force wasn't working. There was just too many degeneracies and dimensions here to explore. Perhaps smashing a hammer to a delicate signal like this just wasn't the solution, and I thought back to that origami flower. The idea left an impression on me. So, over the last year, I've spent some time meditating on this idea. Remember that I told you that planets showing TTVs, wobbling worlds, are very common. Now, these wobbles could be caused by other planets or perhaps moons. Now, as a planet wobbles back and forth, if it's caused by a moon, we can actually pinpoint precisely where the moon should be. For example, if the planet comes into transit later than usual, then the moon must be coming in early, ahead of the planet. Vice versa, if the planet transits earlier than usual, then the moon must be late, behind the planet. So for these wobbling planets, we can look at their transits and say, hey, if the planet comes in over on this side, then the moon should be somewhere over on this side. Okay, that's a start, but it's not enough to create our exomoon fold, because we don't just want to know that it's somewhere over this side, we want to know precisely where it is on this side. Only then could we add together all of these events and create a coherent reconstruction of this composite exomoon signal. Sometimes the universe throws you a bone, gives you a break. And working on this, I had that feeling. You see, in addressing this question, it turns out that the precise location of the moon depends on just a single parameter, the mass ratio between the moon and the planet. If you know that number, and you have a wobbling planet, then you can precisely pinpoint where the moon transit should be each and every time, and thus stack them to form your moon fold, as proved in my new paper. This should make sense because the wobbles of the planet are of course directly controlled by how heavy the moon is. Heavier moon, bigger wobbles. Okay, I know what you're thinking. How do you choose the value for this parameter though? Because it could be anything. I mean, it could be say 1%, kind of similar to the Earth-Moon system, or perhaps it could be 0.01%, more similar to the moons around Jupiter. If you choose the wrong number, then you can't create this beautiful moonfold. Okay, that's true, but we can be persistent. Story of my life, really. And really, that's what we do when we do these planetary folds anyway. Remember that for a planet fold, we actually don't know the planetary period when we start. We really just guess it. And we keep guessing, trying every possibility to see if a signal pops out. That's easy enough because there's really just one parameter to search along, the orbital period of the planet. And here too, with the moon folding technique, there is just one parameter to guess, the mass ratio between the planet and the moon. To show you an example, let's look at a hypothetical Jupiter-sized planet with an Earth-sized moon. We can scan along the mass ratio given by the x-axis here and make a moon fold each time, and then we just see how significant the moon dip is. Of course, most guesses are bad and give no significance, but right at the correct mass ratio, the transit origami technique recovers the signal. If you want to go deeper, I recommend checking out the paper for more examples like this, seeing the technique in action on both simulated and real data. Transit origami is an exciting new technique to add to our arsenal. For the first time, we can reconstruct coherent exomoon folds, something that our exoplanet colleagues have taken for granted for years now. This should pave the way for the vetting of the nature of these TTV systems, wobbling planets. Are they moons or are they simply other planets? Transit origami will help us reveal the underlying culprit for many of these cases, and I can't wait to see that in action. Exomoons remains a challenging field. Look, nobody ever said that looking for a moon around a planet that's around a star that's over 1,000 light years away would be easy. But we know that with our current technology, we can detect worlds as small as our moon. Now, with this new transit origami technique and our previous work on exomoon frequencies, we've never been in a better position to realize this dream. I won't rest until we do. I can't. Whilst exomoons might be my ambition, you surely have your own. Look, it's been 10 years, and I know that after that long, it's easy to give up, too easy. And that nobody would blame you or indeed me for giving up on that dream after so long. But sometimes the secret to success is nothing more complicated than just pure persistence, a refusal to stop. That alone can take you a very long way. So, until the next video, stay thoughtful and stay curious. Thank you so much for watching, everybody. This research was supported by many of you watching right now, donors to our team, the Cool Worlds Lab at Columbia University. In fact, I want to thank our latest supporter, that is my man, Sam Marks. Thank you so much for your support, Sam. If you too want to help us out, then be sure to click the link up above in the description where you can help a real research team looking for planets and moons in the universe. So, until the next video, have a great and cosmically awesome day out there.